Hello everyone, this is group 17 and my name is Kagulo Firdaus. Also my colleague is such as Elvis. He's going to take you through also some parts of this work. We're going to present to you our project, the multi-strategy psychological signal processing for intensive healthcare using the e-signal distillation. Well, we conducted this project under the Department of Computer Science at Makerere University under the guidance of our lecturer, Dr. Galiwango Marvin. First of all, let me take you through the contents of our presentation. Well, first of all, we're going to have a quick overview of our introduction, our related works, followed by the problem statement, also our research objectives and methodology. Then my colleague will discuss the data set, present the results, and conclude with the future directions. And we'll finish the acknowledgements. First of all, we have our related work. Well, in recent years, deep learning has significantly improved e-signal analysis. The CNNs are great at identifying spatial features like the QRS, and the T-waves. Also, our LSTMs capture temporary patterns like the arrhythmias. The distillation is another key technique. It allows us to create smaller models that maintain high accuracy. However, gaps remain. Psychological signals like heart rate, variability, or HRV are rarely integrated, and many distilled models lack clinical explainability. Well, our introduction. ECGs are a vital non-invasive tool for diagnosing heart conditions like arrhythmias, ischemia, and heart failure. However, analyzing ECGs manually is time-consuming, requires expertise, and can vary between observers. While deep learning offers opportunities for automated analysis, but existing models are often computationally heavy and act like black boxes, reducing trust among the clinicians. So our objective is to develop a lightweight and explainable model using the knowledge distillation suitable for real-time use in intensive care settings. We'll have our problem statement. Well, cardiovascular diseases cause over 18 million deaths per year. This is faster and more accurate diagnosis is urgently needed. This means that faster and more accurate diagnosis is urgently needed, yet current deep learning models are too large for wearables and also lack transparency. So all of this, we target an accuracy above 95%, a latency below 50 milliseconds, and also improve clinical explainability. Our computational challenges, patient variability, such as differences in age, gender, and health conditions, adds complexity. Also, noisy data from movement of electrodes can interfere with readings, and moreover, resource constraints mean that powerful models are impractical for wearable or mobile devices. Therefore, our aim is to create a compact, efficient model that delivers high accuracy in real time. Our research questions and objectives. First, our work addresses three main research questions. First, how can we develop a lightweight ECG classification system for real-time analysis? Secondly, how can we integrate psychological signals like the HRV for holistic monitoring? And lastly, how can we improve model interpretability to build clinical trust? Our objectives, our specific objectives were building a robust pre-processing pipeline for noisy ECG signals, also apply knowledge distillation to develop an efficient model, and integrating HRV analysis for stress and anxiety detection, and achieving high accuracy with strong interpretability, particularly in ICU environments. Our research contributions, our main contributions include a pre-processing pipeline that boosts signal quality, improving SNR from 15.2 to 28.7, and a lightweight mobile network, that's the V2-based model, achieving 96.8% accuracy with only 35 milliseconds inference time. Successful integration of HRV analysis with strong negative correlations between HRV and stress and anxiety, and deployment via a Flask API for real-time research by health technicians. And this was our methodology. Well, our methodology involved several key steps. First, we were acquiring ECG data, then pre-processing it to remove noise, extracting meaningful features, developing teacher and student models, using deep learning and knowledge distillation, also evaluating their performance, and finally deploying the solution through an API for easy access. Well, my colleague will take you from there.
Hello guys, this is Elvis, and I'm taking you through the last bit of the presentation. Basically, this is the output or expected results of the of the project. Basically, this is the sample of our data set. As you see, the first 5 and the last 5 rows of our data set. Here we shall see the pre-processing results after performing data pre-processing. That is the signal noise ratio 15.2 before and after, that is 28.7. Then we have the mean squared error, that is 0.00035 and 0.0 after 0.8 after. So you see our visualization, that is the original ECG, you see that above, and the restituted ECG, that is restored, noisy, and degraded. So that shows the original versus the pre-processed one, and therefore pre-processing enhances the quality of the noisy ECG signals from the lead ML-DAO-I and V5. So that also in continuation, we have the accuracy versus the inference time, as you see in the graph, where we have the training compute flow, and as you see the four graphs, the first one varying scaling policy, then resampling, and that is the inference compute flow as seen in this slide. So we have, in continuation, we have shown also the correlation matrix of the ECG futures. We have the D5, the ML-I reads, time per second, and we also show the unnamed values, as you see, ranging from 1 to 0.2. Then also we have a table showing the correlation between HRV and the psychological states, such as stress and anxiety, where stress correlates to negative 0.78 and anxiety negative 0.7. So the visualization below also shows the stressful session of a co-worker, that is versus the stress-free session with other colleague. In continuation to our output, here we illustrate multimodal fusion for ICU monitoring, and basically this enhances diagnostic accuracy, and with it we integrate ECG and blood pressure using multimodal fusion approach. Here the table represents the performance comparison of fusion techniques, where we have fusion method. We have accuracy, sensitivity, and specificity. The future level fusion, as you see, it's accuracy, sensitivity, and specificity plus the decision level fusion and hybrid fusion. So that visualization you see in blue shows the continuous wavelet transform of ECG insights. Basically, the CWT provides a time frequency representation of the ECG signal, revealing a transient features such as arrhythmias. So in continuation, we are showing a CNN model for evaluation, that is in deep learning. Then a contrastive learning model evaluation, as you see, the inputs, the accuracy, and the precision. We see that contrastive learning was better than the GAN model evaluation, its accuracy, the F1 score, and the recall. Then also the running rate of both models. In continuation, output. We have gradient boosting, the SVM, and the knowledge distillation model. As you see there, we are also evaluating them. More output is seen. This is explainable AI output, and the graphs as you see the visualization. We see the SHARP as an explainable AI technique and its impact on the model. Then we shall see the LIME. We also see the partial dependency plots for XAI. So the next steps, our future work, we aim at doing an enhanced generalization and extend the model to diverse populations. We shall also include patients with comorbidities and rare arrhythmias, edge computing optimization. Further, we shall compress the student model for smartphones and wearable sensors, and also we shall add multimodal integration, where we shall combine ECG with PPG for blood or oxygen volume. We have the EEG for brain activity, and also we shall enable holistic health monitoring for clinical deployment and real-world testing in hospital ICUs. Then we shall also add doctor AI collaborative diagnosis in systems. That is our future work. So acknowledgements, we acknowledge authors, we the authors acknowledge deeply and appreciate the invaluable support and guidance by our lecturer, Dr. Marvin Galiwango from Makerere University for his expertise in machine learning and ECG signal processing. We also acknowledge our classmates at Makerere University. Furthermore, we acknowledge the foundational work and the broader research community that we used in our project, and we also extend gratitude to Uniport and the IP office for their contributions. So our conclusion, we enhanced ECG signal quality. Here, we put a robust pre-processing that significantly improves the SNR and reduces the MSE, preparing data for accurate analysis. So we have an efficient and accurate classification where knowledge station uses a lightweight model with comparable accuracy of 96.8% to a complex model that is significantly faster. So we have 35 milliseconds for the lightweight model and 120 milliseconds for the lightweight model. So that means our lightweight model will be more faster. So we have holistic cardiovascular assessment where we integrated HRV analysis with psychological states, and this enables the detection of stress-related cardiovascular anomalies. We also have the limited, in limitations, we have limited psychological scope. Here we focus primarily on stress and anxiety. Other psychological factors may be relevant, but we were unable to. Then we have the dataset general reliability. The performance is validated on specific dataset. So the teacher model computational costs, training a highly capacitative teacher model requires significant resources and also lack of reward clinical validations. So with that, I shall show you our deployed model, a demonstration of it. So this is our demo for the project, and this is the source code as you see. Source code update at app.py, the static files, the templates. So as you see our model. So let me try to run through our code and show you what we hosted on Render. So with a command py app.py, we are able to run this. We are able to run this model py app.py. So let me stop sharing this screen. I had already analyzed signal. So I choose a file. Let me choose client 101, analyze. So it is analyzing. It has analyzed, showing the stress level, the anxiety level, and the depression level. And it also makes a visualization of the patient's ECG results. You can also check another patient. Let's say patient 100. We analyze his data and see the results. As you see, the color changes. And here we show that the stress level is moderate and the anxiety is high, and so is the depression level as it's also moderate. And this is the ECG visualization. So that's all for our deployed model.